week, after we have exam 3, we'll review for the final exam. Okay. So last time we went over section 4.4. So just a few problems in section 4.4. So section 4.4, let's do a quick review. All right, there was 3 logarithm formulas for expansions. There was that the log of a times b is the log of a plus the log of b. Log of a over b was log of a minus log of b, and this goes for any base. And 3, the log of a to the r is r times log of a. And there was also the change of base formula, that the log base b of x is the log base c of x over the log base c of b. So, you can use whatever base you want. Base e, or base 10, which is probably the only buttons for log that you have on your calculator, okay? In this sense, they're all the same, really, because in this change of base formula, if you consider the log to be a function where x is the argument and b is just a constant, then when you use the change of base formula, this is a function, a variable function with variable x, and on the bottom of the fraction is just a constant. So logs are all proportional to each other. All right, so, and I assigned numbers 38, 46, 64. And which ones were assigned, actually? 9 to 45 every third. The 21, that's an interesting problem. So use laws of logarithms to evaluate each expression. The log of 10 to the 10,000. The log of 10 to the 10,000. Well, the exponent here, one identity to remember about logs was that the log base b of b to the m is m, right? Because the log and the exponential functions are inverses of each other, or you can use this one, the log of a to the r is r times log of the a. But anyway, this expression here is 10,000, right? When it just says log, it means log base 10 typically. Log base 10 or no particular base. So, you could do it this way, or you can do it like this. You can bring down that exponent, 10,000, log of 10, close. All right, log base 10 of 10 is just 1. Times 1. All right, so this is the log of 10,000, which is 10 to the 5th. So log base 10 of 10 to the 5th, which is just 5, using that if you want. Or you can, use number 3 here, bring the 5 down. Log base 10 of 10 is 1. So final answer there is 5. So that's a cute problem. So number 38. So number, let's say 36 and 37. So 36 is s to the 5th over 7t squared. Log base 2. So it's asking you to expand this expression. Expand means to 7t squared. 10. So expand this expression. That means get all of the multiplication, division, and exponentiation out from the inside the argument of the log as much as possible. Right. Well, first we have a fraction. So the log of a over b is the log of a minus the log of b. That's number 2 there. Log of a over b is log of a minus log of b. So we applied that. Now this one is a product, right? So this one is a product. So the product becomes a sum of logs. Like that. Now, of course, the log of a times b is the log of a plus the log of b, like that. Log of a times b is log of a plus the log of b. But since we're subtracting it, we got to make sure, we're replacing one term with 2 terms. So we have to make sure that we put parentheses there. Okay, so that's the law number 1 there. So then the exponent using law number 3 comes down. So this is 5 log, it's all log base 2. Log base 2 of s minus, this one is just log base 2 of 7. And this one, the 2 exponent comes down in front. And that would be as much as you can expand it. Okay. Number 37, similar sort of problem. Log base 3 of, so again, expand. So log base 3 of 3x to the 5th square root over y. So first of all, we have a fraction, log a over b. So I'm going to do the log of a minus the log of b, like that. Okay, now we've got this square root. Remember, square root is an exponent, right? So that whole thing is a 1/2 exponent. So this is 3x to the 5th to the 1/2, like that, minus log base 3 of y. So now either I can distribute the exponent through here, or I can bring the exponent outside. I'll just bring the exponent outside. So this is 1/2 the log of 3, log base 3, of 3x to the fifth minus log base 3 of y. Now I have a product. So the log of a product is the sum of the logs. Now, since we're replacing one term with two terms, I have to make sure I put parentheses there if I'm multiplying it by something. Right, and now I'll distribute the 1/2 and I'll bring down that exponent, or I'll do it in 2 steps. Log base 3 of 3 plus bring down this exponent 5 times log base 3 of x minus log base 3 of y. Now I'll distribute through. And that would be a final answer. Okay, so number 38, pretty similar to that one. Very similar to number 37 that we just did. 46. So 46 is again somewhat similar to I mean, it's very close to 38 for number 46. Let's do number 45. So again, expand. So we have the log base, no base, so that means base 10, just log. Fourth root of x squared plus y squared. All right, remember a fourth root is the same as a 1/4 exponent. Okay, so remember, let me write it up here. A to the 1 over n equals the nth root of a. That's simply, right, the definition of what an nth root is. And then if you have any other rational exponent, a to the m over n, that's equal to the nth root of a to the m, which is the same as the nth root of a, that whole thing, to the m. Okay, so, and again, the fractional exponent is the preferred notation. Really, one does not use these fourth root and third root. One uses the square root notation, right? But like third root, fourth root, these are not really used too much. I mean, normally you just, when you have the fourth root of x, people will just write x to the 1/4. Okay, this is the more common notation. But anyway, so not that it's never used, sometimes it is. Like right here, we just used it. So this becomes a 1/4 exponent, and then the exponent comes out front. Then what? Trick question. What else can we do? What else can we do with that? Nothing. Okay, when you have a sum inside the log, you can do nothing with it. Okay, other than deal with it as it is. Okay, there's no way to split apart log a plus b. Log a times b is equal to the log of a times, or plus the log of b. Log A times B is log of A plus log of B. Log A plus B, nothing. There's no help with that one. Okay, so that's the final answer here. All right. What else in this section? I also assigned number 64. What 64 is like recombining these things. Oh no, change the base formula. Sorry. Use your calculator to calculate the following. So say log base 4 of 125. So log base 4 of 125. Okay, so there is no log base 4 button on your calculator. I mean, typically your calculator will have log and ln. You can use either one. Okay, whichever one you like. So this is equal to the natural log of 125 over the natural log of 4, which is going to be, and then your log button might use reverse notation like this one does, 125 natural log divided by 4 natural log. So 3.48289. Use 6 decimal places of accuracy. That's 6 decimal places. No, that's 1, 2, 3, 4, 5. No, I need one more. 9, 2. Or you can do log base 4 of 125 is equal to log 125. That's log base 10 over log base 10 of 4. Either one is fine. It will give you the exact same answer. So 125 log divided by 4 log is exactly the same thing. All right, natural log 125 divided by natural log 4. Log base 10, 125 divided by log base 10 of 4, same answer. All right, so that's 3.482892. All right, so different bases, they're not a problem. You can do them on your calculator easily with this change of base formula. All right. So that's all in that we really need to cover in section 4.4. Where these tools that we've looked at for logs and exponential functions start to become useful is in this section 4.5, and we can actually start doing some interesting problems dealing with logs and exponential functions. So section 4.5. Equations with logs and exponents. So let's write down what we know so far. So far we know the following. So we know that log of, and this is for any base, and a plus b, log a times b is log of a plus the log of b. Log of a over b is equal to the log of a minus the log of b. Log of a to the r is r times log of a, and that's an important one. So other things we know, the log base b of b to the x is just x, and x to the log base b, b to the log base b of x is x. And this was, again, the notion that exponential function and exponential function with base b and the log base b, they're inverse functions of each other. So they cancel each other out, so to speak. What else? I think those were all of them, right? Yeah, so far we know these, there's also the change of base formula, right? Log base b of x is log of x over log of b, which is the same as natural log of x over natural log of b. Now, when you're solving equations with exponential functions, oftentimes you can use whichever base you want. Sometimes you might want to use a different base, but anyway, so let's solve for x. So e to the 3x plus 5 is equal to 7. E to the 3x plus 5 equals 7. All right, so let's look at this right here. Let's write it in terms of e. So log base b of b to the x is x. When it's just with e, so the log base e of e to the x is just x. And e to the ln x is equal to x. So it's a little cleaner looking when you just look at it with the natural log. Right, so this is for any base right here, these two formulae. Right, but when you translate them to log base e or natural log, they look like that. Okay, a little cleaner looking. Okay, so if you want to solve for x, basically you got to get the x out of the exponent. To get the x out of the exponent, you want to get rid of the e. Right, so what you do is apply whichever log function you want. So since it's got an e there, we'll use natural log. Apply natural log of e to, or natural log function to both sides of the equations. Right, because a is equal to b, the natural log of a is equal to the natural log of b. A is equal to b, so the natural log of a is equal to the natural log of b. But this one now comes into play. Right, the natural log of e to whatever, the natural log of e to the x is just x. So here the natural log of e to the 3x plus 5 is just 3x plus 5. And natural log of 7 is just 7. Right? We apply the, so to get the x out of the exponent, we apply natural log to both sides, and we get this. But now the log and the exponent, natural log and the exponent, just cancel each other out. And I'm left with 3x plus 5. So now I can solve for x. So x is natural log of 7 minus 5 over 3. And if you want, you can get an answer for that. So it's 7 natural log minus 5 divided by 3. So minus 1.018. Okay, so that's a simple equation where we have an exponential function equal to a constant. Exponential function equal to a constant, and you want to solve for the x in that exponential function. So here's something a little bit different. Although it boils down to the same thing. So again, solve for x. So suppose I have e to the 2x minus e to the x minus 12 equals 0. Right, well, remember also when dealing with exponential functions, a to the b to the c, like this, is a to the b c. A to the b to the c is a to the b, all to the c powers a to the b times c. So using this in reverse, this is e to the x squared minus e to the x minus 12 equals 0, right? E to the 2x is e to the x squared. Okay, so so I've got a quadratic equation. My variable isn't x, my variable is e to the x, right? But I can still attempt to factor this thing. So this would be e to the x minus 4 times e to the x plus 3 equals 0. Right? So it's a quadratic-like equation, right? I mean, it's blank squared minus blank minus 12. And instead of like x squared minus x minus 12, right? We've done these before. So, and just like x squared minus x minus 12 is equal to x minus 4 times x plus 3, this one is e to the x minus 4 times e to the x plus 3. Okay? All right. So this means e to the x minus 4 equals 0, or e to the x plus 3 equals 0. Now, what I can do is isolate the e to the x. Now, just like in the last problem, I can now apply the natural log to each side of the equation. So what I did is I solved for e to the x. Once I have e to the x equal to whatever, then I can write the natural log of e to the x is the natural log of whatever, and then this becomes x. Right? So let me just write that down. So e to the x, well, not remember, but typical. E to the x equals something. You then write natural log of e to the x equals something. But then this becomes or equals natural log of something. And then this just becomes x on the left equal to something. But what's wrong with this one here? What's wrong with this one here? So e to the x equals 4, that's fine. Natural log of e to the x equals natural log of 4. So this means x is natural log of 4. So that's good. But what about this one? I mean, why can't I just do the same thing then? I could, but...
It's negative.
Yeah, exponential functions are always positive. They're never negative. They're negative 0. Unless it was like this. If it was minus e to the x equals minus 3, that's fine. You know, then you just have e to the x is positive 3. All right, so if you had this, that would be okay. But the exponential function itself, right, a to the x is always positive. All right, so put that on the side. Side note, a to the x is strictly bigger than 0. Not bigger than or equal to, strictly bigger than 0. So this one is impossible, so no solution. So x equals ln 4. That's the solution there. There should probably be some in the text that are kind of like that. Let's see. Let's look at 27. So number 27 in the book, it doesn't use e. It uses a log base 10. That's fine. So solve for x again. 4 times 1 plus 10 to the 5x equals 9. So we want to get it down to this. We want to get it down to this kind of thing. E to the x, in this case 10 to the x. 10 to the x equals something. 10 to the x equals something. So essentially you want to solve for the exponential expression first. So solve for the exponential 10 to the 5x first, then apply log base 10 to both sides of the equation. So I'll divide by 4 first off. So 1 plus 10 to the 5x equals 9/4. And then I'll subtract 1 from each side. So 9/4 minus 1, 5/4. Now I can apply log to each side. It's base 10, so, you know, I mean, it would be a natural choice to use the log base 10 if you wanted. You don't have to. You can use the natural log. Let's start with the log base 10. I'll show you how you can use the natural log. So let's apply log base 10 to each side. Right, so first thing we did was to solve for the exponential 10 to the 5x first. Then apply log to each side. So this was step 1. All right, so now I apply this to each side. So I have log base 10 of 10 to the 5x. That's equal to what? I have log base 10 of 10 to the 5x. That's going to be equal to what?
5x.
Just 5x, right? That's why we apply the log to each side. It's the inverse function. So this is just 5x. This is log of 5/4. So now divide by 5. So this is approximately equal to, let us get an answer. So, so 5 divided by 4, 1.2, right? And then we're going to apply log base 10, and then divide this whole thing by 5. So we get 0.019382. 0.019382. Okay, so that's your final answer. But you didn't have to use log base 10. Right? Natural log will suffice. Will work too. So let's apply the natural log to both sides. So this is natural log. Well, let's go down here and do it. So let's solve it again. So this becomes natural log of 10 to the 5x equals natural log of 5/4. So we solve with natural log instead, and you apply the formula that natural log of 10 to the r is r natural log of 10. All right, so that exponent formula. So the logarithm property, right? Log base b, whatever base it is, log of a to the r is r times log of a. So instead of doing this, the log base 10 cancels out with the 10 to the 5x and just leaves that. It's a little less clean, and you have to use this thing here. But it still works. It still works just fine. So the exponent comes out front. 5x natural log of 10 is equal to natural log of 5/4. And now you just divide. Right? So I'm going to divide by natural log of 10. So 5x equals natural log 5/4 over natural log of 10. Now divide by 5. Whoops. So this is natural log, I should have done it all in one go, I guess. 5/4. Let's do it all in one go. It's more confusing this way. So I'm going to divide both sides by 5 times natural log of 10. Right, so this becomes x is equal to natural log 5/4 divided by 5 times natural log of 10. I mean, it looks different than that, right? But you'll see it's the same thing, right? You'll see it's the same. You could apply the change of base formula, right? I mean, it's 1/5. Applying the change of base formula, it's 1/5 log base 10 of 5/4 right here. Applying the change of base formula, or just plug it into your calculator and check it out. So 5/4, 5 divided by 4, natural log divided by 5 equals this, divided by 10 natural log, right? Equals, there it is, oops, I did something wrong. Try that again. What are we looking for? 0.01. Yeah. So 5 divided by 4 is this. Natural log divided by 5 is that, divided by 10 natural log equals 0.019382. Right, same answer as before. All right, so whichever log you prefer, log base 10 or log base e, depending on what context you're working in. You know, one is used more often than the other. Um, Most sort of like math and physics. If you're, I think like if you're looking at sort of economics and finance type situations, people use log base 10 more. But in physics, just pure math, people use log base, natural log base e more. So that's number 27. How about 29? Well, let's use a different. How about 31? Ooh, 31 is a tricky one. Oh, yeah, that's a hard one. That's a hard one. Yeah, that one's tough. I'll show you that one. How about 33? 33 is a good one. 33. All right, so solve for x. So 5 to the x equals 4 to the x plus 1. So here we have two exponential expressions on both sides of the equation. All right, so we're getting a lot of different types of equations here. We're going to spend like more time on this section. We're going to spend the whole week on this section essentially. But you mean, so you know, we'll go over this stuff. We'll have plenty of examples. A lot of different types of equations, but we'll do plenty of examples. Solve for x. So we got 5 to the x equals 4 to the x plus 1. Well, already we've essentially solved for the exponential expressions. By the way, there's no way to combine. You could subtract the 4 to the x plus 1 from each side, but there's no way to combine these things. You just can't add these guys together. You can't add these guys together in any way. It doesn't work. Okay, so what you do here, well, I mean, you just apply a log to each side, whichever log you want. Well, natural log or log base 10, right? And then the exponent comes down in front. Like that. All right, so I'm going to move my terms with x to the other side, and the terms without x are going to stay on the right. So first I'm going to distribute here. So I'm going to write it like this now. So ln 5 times x is equal to ln 4 times x plus ln 4, like that. Now I'm going to move this over here, subtract it from each side. Okay, natural log of 4 and natural log of 5 are constants. So we're just treating them as such. I mean, I know it's not just like a number like 3 or 4 just by itself, but it is just a number. Okay, so we're just treating it as a coefficient for x. Now I can factor out x from each side. ln 5 minus ln 4 times x is equal to ln 4. And now I divide both sides by this expression here. And that's the answer. Right? These are all constants, so that's the answer right there. Or, you can plug it into your calculator and see. and see what the answer would be more, more specifically as a decimal approximation. But this would be a final answer, right? Everything is a constant here. By the way, ln A minus ln B, there's nothing you can do with that. The log of A minus the log, or no, I'm sorry. No, that one's a fraction. That's ln 5/4. But I mean, it doesn't matter because you're gonna just put it into your calculator. If it was ln 5 minus 4, that's what I was thinking. So you could combine this natural log 5/4, but I wouldn't bother with that. I would just do the division as it is. So we've got natural log of 4. So 4. Oh, by the way, if you don't want to use a calculator, if you want to use, your web browser, you can use that. Or you can use that Wolfram Alpha, as a way of double checking yourself. So you can do it right here in the search bar, or go to Wolfram Alpha. So natural log of 4 divided by natural log of, 5 minus 4, like that. Right, and it'll give you the answer right away, right there. So why did it say log? I put natural log. Why is it doing that? It doesn't matter which one. That's another way. That's an alternative form. But anyway, the decimal approximation, 6.21256. 6.21256. So let's look at that on our calculator instead. So it's easier to make a mistake on the calculator with the web browser or with Wolfram Alpha. With the web browser or with Wolfram Alpha, like it confirms to you what you actually typed, right? So it's easier to do, or you can do it here, ln 5 or ln 4 divided by ln 5 minus ln 4. So I don't like using Google too much for these things because it gives you an inline expression. There's, Wolfram Alpha gives you something much nicer looking right here. But here, it read the input as ln 4 divided by ln 5 minus ln 4, 6.212567. Sometimes it's easy to make a mistake on the calculator, so you might want to check yourself once in a while in a web browser to make sure you're doing it right. So 4 natural log divided by, and here's where it's weird because you got to use these parentheses here. 5 natural log minus 4 natural log, close parentheses. So this is the expression I've got here. So this one is not too bad, this calculator, because it's sort of confirming to you what you've typed in. 6.212567. And you don't have to use the natural log there. You can use the log base 10. That'll work just as well. Okay. Either or. Just, whichever one you're using, stick with that one throughout the calculation.
How would it look different if we used log base 10 from the beginning?
Oh, nothing. Just, it would look exactly the same. Just cross out, just replace ln with log. It would look exactly the same. All right, we can do it. Or log of 5 to the x log 4 to the x plus 1. The only time one would be preferable over the other is if the base you're using is base e or base 10. Like you have an exponential expression 10 to the x or an exponential expression e to the x. In that case, like log base 10 might be a better choice because the calculation would be simpler, or natural log for this. But here we have some funny bases. We have base 5 and base 4, so it doesn't matter. It's going to be just as it's not going to be any easier using one base than the other. Any less messy, I guess. So here I'm gonna move the constant in the front. And distribute the log base 4 through here. Subtract this from each side. Factor out x. And then divide by log 5 minus log 4. Like that. And you can stick that in your calculator and you'll see that you get the exact same answer. Well, actually, in Wolfram Alpha, they did it with log base 10, I think. Oh, log x is the natural logarithm. Oh, that's weird. Why would they use that? All right, well, let's do it on our calculator. So 4 log divided by parentheses 5 log minus 4 log, close parentheses. Okay, so that's the expression we're calculating right up top there, and 6.21256. Same answer, of course. It's a weird one. Let's not do 31. Let's do 35. So 35, 2 to the 3x plus 1 equals 3 to the x minus 2. Solve for x. So similar to the last problem, I'm just going to take the natural log of both sides. And now the exponents come down in front. Now I'm going to distribute the natural log of 2 through this sum and the natural log of 3 through that sum. So this is 3 times the natural log of 2 times x plus the natural log of 2. This is going to be the natural log of 3 times x minus 2 times the natural log of 3. This term has an x and this term has an x. This term does not have an x. This term does not have an x. All the terms with x, I bring them to the left. All the terms without, I move them to the right. So this is 3 natural log of 2 times x minus natural log of 3 times x is equal to minus 2 natural log of 3 minus natural log of 2. All right, so I moved this one to the right. This one, I moved it to the left. Factor out an x on the left. Three natural log of 2 minus natural log of 3. Well, that times x. Minus 2 natural log of 3 minus natural log of 2. Divide both sides by this expression here, and I have x equal to over 3 natural log of 2 minus natural log of 3. I'm going to factor the negative out of the numerator. 2 natural log of 3 plus natural log of 2 over 3 natural log of 2 minus natural log of 3. So that's the exact answer right there. So I'm going to put that into the calculator. Whoops. And get a decimal approximation for that. That one. That one. All right, so 2 times 3 natural log plus 2 natural log. Okay, so I've already made a mistake. I'm going to need parentheses around that whole expression there. So 2 times 3 natural log plus 2 natural log, close parentheses. So there's my numerator. 2 times 3 natural log plus 2 times 3 natural log 3. No, 2 times the natural log of 3 plus the natural log of 2 divided by 3 natural log of 2 minus 3 natural log, close parentheses. So that's what I'm looking at right here. 2 times natural log of 3 plus natural log of 2 divided by 3 times natural log of 2 minus natural log of 3. And you need all those parentheses there because it won't understand the division if you don't. If you leave the parentheses out, it'll be something like this. Right, so if you leave the parentheses out on the top, it'll only apply the division to the natural log of 2. So it has to be typed in like that. And that's equal to 2.9468, or negative. Okay. Let's look at some examples in these word problems. We've been looking at these modeling problems where we had, these compound interest problems and also these half-life, radioactive decay type problems. And you'll see how these techniques are useful here. 89. So $5,000 is invested in an account that pays 8.5% interest per year, compounded quarterly. So $5,000 is invested at 8.5% compounded quarterly. So 4 times per year. Find the amount that the investment is worth after 3 years. So that's part A. How much is the investment worth after 3 years? Well, this is just like how the problems we were looking at in section 4.1, I guess it was. So A of t is equal to, and then the compounded interest rate formula tells you it's 5,000 times 1 plus the interest rate, 0.085, over the number of compounding periods to the 4t, like that. Right, so after 3 years, it's 5,000 times 1 plus 0.085 over 4 to the 12th. Okay, so let's get a quick number for that. So 5,000 times 1 plus 0.85 divided by 4 is 12. So 50,000. Oh, 85. 0.85. Something was off. So 6,435 and 9 cents. And of course, with these types of things, you can always round off to the nearest penny. But point B is the more interesting question. How long does it take for the investment to double? So how long does it take for the investment to double in value? Right? In other words, you're looking for the number of years it takes for 5,000 to become 10,000. So in this case, how many years for the investment value at $10,000? Well, so you set A of t, to be equal to 10,000 is equal to 5,000, 1 plus 0.085 over 4 to the 4t, and now solve for t. Okay, well, it's 10:57, we gotta go. I'll finish that one up, and we'll look at it tomorrow as well. Okay. All right, guys. Have a good day, and don't forget about the assignments that are due tonight. And I will see you tomorrow. Email me with any questions or concerns.